네, 한성민 씨 안녕하세요. 아홉 시가 되면 시작하도록 하죠. 네, 정상목 씨 안녕하세요. 네, 박건우 씨 안녕하세요. 자, 우리 9시 되면 수업을 시작하도록 합시다. Okay, so it's 9 o'clock and good morning everyone. So how was your homework 6? How was your homework 6? So I think that if you have done it properly, then you will find that some of your phi function with different boundary conditions up to n will be the same with the one where all terminals are biased with 1 volt. So you will find that actually this is just 1 over your simulation domain, and some of your functions, solution functions, will be just identically 1 unit t over your simulation domain. So I hope that already you have found that one. Also you can feel that this is not that difficult to show it to show it in an analytical way. Okay, so now let's come back. Oh, by the way, if you have any difficulty or any question during performing your homework number 6, then please let me know. Once you have any question, then please let me know, then I can answer your question, and only after that we can proceed to lecture 7. Lecture 7 will be devoted to the continue the discussion about how can you treat multi-region cases. So students, so please leave your message whether you have any question for homework number 6 or whatever covered in this lecture course. Okay, thank you. Thank you for your feedback. And how about other students? Yes, okay, thank you. Okay, then if you don't have any question on homework number 6, then let's continue the discussion in lecture 6. What was it? So we have thought about how can you assign unknown variables for different regions, or even inside the region we can have some selection for unknown variables. So think about this is region 1 and region 2. Then in many cases we are interested with electrostatic potential and electron density and hole density. So the simplest way is just to define electrostatic potential, electron density and hole density in region 1 and region 2, regardless the property of the material for region 1 and region 2. So even that is a metal insulator, we can try to introduce electron density and hole density in it and just neglect them. That can be one possibility. However, we have just to conclude that in order to maximize the efficiency of our approach, then we have to be a little bit more careful whether that physical quantity is really required in that region. So if one region is just an insulator one, then we don't have to have, for example, electron density and hole density. And we have thought about more examples like lattice temperature and electron temperature and hole temperature. In this case, yes, still this one can be defined all over our simulation domain. However, the temperature for electron and temperature for holes, that they have meanings only when we have well-defined electron density and hole density. So if for certain reason, if we don't have any electron density or hole density, then it is not reasonable to define electron temperature or hole temperature. Also, another example we can consider is quantum correction. So-called quantum potential, and also it is related with electron density or hole density. It plays a role to modulate the shape of our electron gas, and it is closely related with electron and hole. So you know that if there is a certain quantity related with the electron, then it is better to consider it only for semiconductor materials. And also, if you have any quantity related with holes, then also it is reasonable to think about some regions which have meaningful hole density. And that is region-based constellation. And at the end of our lecture 6, we have introduced even more advanced example like n sub t. This is once again trapped electron density. And we know that even in a semiconductor region, this NT can have certain meanings for specific localized point. So otherwise, if there is one single electron here, then considering trapped electron density in this point or that point doesn't make any sense in this case. So simply speaking, when we consider more general structure, we should be a little bit more careful about defining variables. So that was the main lesson taken from our previous lecture. Then now think about this case. So, and maybe you remember that actually at the end of our lecture, then we prepared a certain really simple example with a limited number. But anyway, I think that is really good to get some feeling about it. 1, 2, 3, 4, 5, 6, 7. You remember this guy? And yes, we had introduced top gate and bottom gate and introduced 3 different regions like yes and yes. Although that is really crudely discretized, however, you really understand this is basically the double gate structure. So you can calculate a certain thing with this really simplified one. And you remember that we have assigned our unknown variables like electron density and hole density and electrostatic potential for this really simple structure. So if we just follow the simplest approach, then you will find that okay, this guy will generate 3 times the number of points, so 7. So we will have 21. You remember it. And for electrostatic potential or for our newer more advanced approach, so NP, this one has only 3 variables for this silicon region in center. This is silicon and this is oxide and this is oxide. Then you will have yes 3, 3, 4. This is silicon region, and we will have 7. And you remember that the number becomes just 13 instead of 7. So that will be a good way to reduce the number of unknown variables. Up to now, it was just a review of our previous lecture. So do you remember all contents in lecture 6? Then if you have any question during the review process, then please let me know. And if there is no further question, then let's move to today's main lecture. Okay, then our main lecture start from this one. Yes, now we have just 7 points. Then let's think about the real case. Yes, so now we introduce variables. So for our unknown variable, a vector for unknown variable. This is a vector for unknown variables. So today's topic is how can we define this vector and how can we access for each entry of this vector. Okay, so think about this one. We have 3 regions, multiple regions are there. So say this is 1, 2, 3, 4, 5, 6, 7. Then maybe if we collect the unknown variables, then it is very easy to say, okay, we will introduce 7 unknown variables. For example, phi for electrostatic potential, phi1, phi2, phi3, up to phi7. So I wanted to ask to our students about this description. So now only for electrostatic potential, I have introduced 7 unknown variables. But actually, this is not the case. It's not the case in the realistic simulation. So, do you feel something still to be improved in this scheme? So, I wanted to ask all of you about any opinion on this way to set the 7 variables for electrostatic potential. Okay, so everybody please respond to me. So Mr. Han, thank you for your feedback. It means that yes, we will talk about different variables like electrostatic potential, electron density, and hole density. And first, let's consider electrostatic potential. In this structure, we have 7 vertex points. Yes, we have 7 vertices, and therefore, if we try to assign variables electrostatic potential at certain node, vertex node, then we are trying now to assign 7 different electrostatic potentials. So starting from phi1 up to phi7, and the meaning of phi1 to phi7, that is quite straightforward. For example, phi1 is the electrostatic potential assigned for vertex node 1. Phi2 is the electrostatic potential assigned at vertex node 2. Phi3 is the electrostatic potential assigned to phi of vertex number 3. So in this way. However, what I'm asking you, all of you guys, is this is not a general way or more convenient way to discretize our system. So we should improve this treatment. So I think that sounds a little weird because this is so straightforward. We have 7 points and 7 unknowns for them. So my question is, please think about what is the possible improvement we can take from this simple structure. So if you have no idea, then please let me know. You cannot find for why the improvement, but anyway, it is good to have your feedback. So please, everybody. So this time you say that electrostatic potential for the silicon region can be separately extracted. So it means that let's first think about Mr. Hans' approach. So it means that we can think about, yes, among potential, we think silicon, and silicon, and 3, 4, 5. This vector, small vector, is separately considered according to Mr. Hans' approach. And Mr. Park, you say that in a vector, potential and density. Yes, however, Mr. Park, that is, of course, that is really good. You are right. However, my question right now is just to concentrate on electrostatic potential. So of course we have to consider electron density and hole density later, but I'm asking just to the electrostatic potential. Even in that case, we can make an improvement. Okay. Anyway, thank you for your feedback. And how about Mr. Chung? So, the potential is linearly varying in the oxide region. So we can define only this point and also this point. Oh, that is also very interesting approach. Okay, good, quite good. But you know that this is just a one-dimensional example. Yes, but anyway, that is really good approach. Okay, interesting, quite interesting. But let's say that you have to solve this type of structure. So two-dimensional electron two-dimensional cross-section of your certain device. So let's say that now you have the surrounding gate over your system, and this is fully made of oxide and silicon, and say that now you have certain points here and here and here, here. So I will just draw part of it. So, Mr. Jong, I think that your suggestion is very interesting. So, if we are working with just one-dimensional structure, then of course that can be a really good way to reduce the number of grid points. However, we are not talking about how can you make an efficient mesh. So we assume that mesh is just given. Yes. So for example here 7. Then my question is how can we assign unknown variables? That was my question. But anyway, it was really interesting, and I have prepared a counter example for your method. Yes, so this is two-dimensional case. Yes, and here we have a certain surface potential, and here we have the potential governed by the gate voltage. However, yes, along this line and this line and along this line and along any line, there is no guarantee that the potential varies linearly when we change the coordinate. Yes, so Mr. Chung, so although your suggestion is quite interesting and intuitive, however, in general, potential can vary non-linearly, unfortunately. So that's the reason why we cannot accept that method. But anyway, that was really interesting and quite efficient. So it means that actually when we try to build the real mesh, usually we don't have to spend much or many mesh points for oxide regions. Once that is guaranteed that the potential varies linearly. Thank you. However, that stimulate me to introduce a few more concerns. One is, yes, so in this oxide region, it is in many cases we can in many cases we can linear potential, linearly varying potential. However, I wanted to stress that if there is certain charges even in the oxide region, then potential does not vary linearly. I mean that for some cases we can consider the oxide trap, the trap located in the oxide, which is very important for the reliability or noise simulation. Also, for example, yes, so or not just trap, but we can also consider fixed potential here. And for some cases, we can have heterostructure for insulating layers. For example, if we consider, I want to say, if we consider some advanced gate oxide stack, it is no longer just a pure silicon or silicon dioxide. We can introduce many low K material and high K material, and they can have different composition. So in reality, this insulator region can be divided into many sub structures. So therefore we have to introduce also many substructures, and for each of them we can have a certain imperfection. So in some cases we have to introduce charges in this bulk, or sometimes we have to introduce certain interface charge between two structures, two layers. I mean that low K material and high K material. Between them, unavoidably, we have to introduce a certain amount of a fixed charge. So if we have such kind of thing, then the discretization of our insulator region can be more complicated. But anyway, Mr. Jung, thank you really thank you for your nice suggestion. And let's come back to Mr. Park once again. Yes, as I told you before, your suggestion is quite right. So of course we have to consider a grand vector which contains everything at the end of our consideration. However, for a while, let's just concentrate on the electrostatic potential only. And let's come back to Mr. Han. Yes, you are now suggesting this one, and this one, your answer is quite close to my answer. So let's discuss it a little more. So, okay. So anyway, thank you for your really creative comments or opinions. I never expected such kind of a variety of your answers, and it is really good to have your feedback. So if you have any comments on my response to your feedback, then please let me know. If you don't, then I will just move to my answer. In reality, we do not introduce 7 unknown variables, the electrostatic potential, for this problem. In reality, we introduce more. Here we have 3 points, and here we have 3 points, and here we have 3 points. You know that this is oxide region, and then this is silicon, and this is oxide. And if we just label the vertex number, then 1, 2, 3, 3, 4, 5, 5, 6, 7. So what we have to do is the potential at vertex number 1 and oxide, and vertex number 2 oxide. And please concentrate now. Here we introduce oxide region and vertex 3. Please have a look at this one. In this case, we can think that silicon region and vertex number 3. That's the point here. So we can define silicon region at vertex number 5 and oxide region and vertex number 5. I think that's the point. Yes, this concept is important. It means that even for a vertex, we must define for okay, So can you read it here? So even for a single vertex, we have to introduce multiple variables if some multiple regions are eligible to have that material or that unknown variable. Okay, so maybe it seems to be a little bit complicated, but let's think about this one. I have found that some of you have introduced very interesting structure like this. Oh, circle, and this is divided into several pieces. Then now let's define electrostatic potential. Yes, potential, electrostatic potential and potential. It means that according to my suggestion here in the lower part, then if we have, for example, a vortex here, then we have to introduce two potential variables. Are you with me? So, for example, in this case also we need two. Then how about this central point? In this case we have to introduce four. If all of them can have a potential, then we have to introduce four potential variables. That is the point. Of course, you feel that that is really, how can I say, tedious and inefficient, because you know that for that meeting point, like a point where two regions are meeting together, or even at the center point where four different regions are meeting together, we can say that actually the potential from one region and another region will be the same. So it is really obvious that, for example, these four potential variables is just can be considered of waste of three unknown variables. So we are just introducing redundant three variables because there is only one single real electrostatic potential, and that value is shared for four different regions. So actually three of them are redundant. We don't have to introduce them. But point is, this is not the case. No, we don't have, so we cannot pursue this efficient way. Oh, in many cases, I always suggest to you that try to find out an efficient way. However, in this part, I'm just saying instead of considering the maximum efficiency, just let your regions, each region, have its own unknown variable. So are you with me? So now if we are coming back to the answer of my question is, let me just repeat again. Instead of seven potential variables, now we have to introduce 9 potential variables, and additional 2 was introduced here, these interface points. Now potential at vertex number 3 is split into certain region, oxide region and silicon region, and also this guy is introduced or split into silicon 1 and oxide 1. That is the point. So now you have more unknown variables, two more redundant unknown variables, and in large system. So now if we collect all of our unknown variables, then instead of number 13 we previously expected 3.3 plus 7 plus 3 plus 3 due to electrostatic potential, electron density, and hole density, the number should be 15. Why? We have 3, 3, and 3. So, are you guys all with me? Yeah. So then let me just give you a quick question. Still think about a double gate structure, and now we have introduced such kind of thing. So we have just a boundary point for this top oxide region, and also boundary point for this lower oxide region, and between them here we have 100. Oh, so instead of 100, let's say the 101 point. Then let's try to estimate the number of real unknown variables when we consider the electrostatic potential, electron density, and hole density in our simulation. What will be the number of our all unknown variables? That is my question. Okay, could you please calculate it and leave your answer to here? So to here means that chatting window, then I can read. Okay, so okay, let's consider the answer. First of all, we have to consider electrostatic potential and electron density and hole density. For electron density, we will need 101. Starting from this point and ending at this point, we will need 101. And hole, we will have 101 once again. And in the case of our electrostatic potential, we have 2 for this top oxide region and 2 for our bottom bottom oxide region, and again 101. So the total number will be 307, and I think that maybe so Mr. Jung is a little bit confused with the other one. Oh, so point is, when you say 103, so 103 cannot appear. So 103, I mean that for electrostatic potential, the number should be 105. That's the point. I mean that here, entire number of points is 103, but point is since we have here interface, so this guy and this guy can contribute to 2 points and 2 points, so the number will be 105. And yes, so are you all with me, especially Mr. Chung? So you understand, do you understand the correct answer? So please let me know. Or if you have any question on my answer, then of course it is encouraged to give you your argument. So then I will happily discuss with you on this stuff. Okay, great. Then now you understand the situation. Now let's say that we have this case. Now we have 307 points, and eventually you will make a vector. Okay, let's say that this vector is called as x, for example. Since you are all working with MATLAB, so I think that you are not very unfamiliar with this convention. For example, this one, semicolon. But anyway, let's say that the size of x vector will be now 307,1. Okay. Then question is, what is the physical meaning of x1 or any number? 100 and 307. So it is really depends on your choice. Actually, you can define in different ways. For example, one way we can think is yes. First, define electrostatic potential, and next define electron density, and finally define hole density. That can be one possibility. I'm not saying that this is the real solution you have to have, and also we can think about this way. For example, let's first consider oxidalism, top oxidalism, and let's consider now central siliconism, and let's consider the lower bottom oxidalism, and inside it also we can say phi n p, phi n p, phi. I made a mistake. So sorry about that. So for, of course, sorry about that. I made a mistake. For oxidalism, it is not possible for us to define electron density. So sorry about that. I made real mistakes here. So now we can think that this can be another way to define unknown variables. And another possibility is, I'm introducing, sorry about that. 네, 수업 중입니다. 네. Okay, sorry about that. Sorry for the interruption. So I have a phone call from the office, um, school office. But anyway, let's come back to our discussion once again. The third possibility is okay. We will just keep the regional way to large separation. And yes, here phi and phi is not that difficult. And in this silicon region, we can think that vertex wise assignment. I mean that it looks like this. For that phi and p for certain node. For example, if we just take this right example, then this is corresponding to vertex 3 and phi and p for vertex 4 and finally phi and p for vertex 5. So this is just different ways, and of course there is no strong preference from our side. Of course, I think that the performance of our matrix solver really depends on the way of this variable arrangement. So certainly some of them will poorly perform and some of them will perform much better. So that is sure. However, anyhow, in our case, we can select any of them, then you can select any of them. But still once again, let's try to say something. So now ask yourself, what is the physical meaning of x1? Yes, depending on your way for specifying something, then for example, in this case, that will be, yes, so in this case, that will be electrostatic potential at node number 1. Okay, node number 1. Node number 1. Great. And how about our for example 100th value? In this case, we will have, yes, in this case we will have just potential at 100. No, actually not. A little bit tricky, but you know that in this potential, actually we can define phi 1, phi 2 twice and go this way. So I think that if we are really talking about the 100th elements of our unknown variable vector x, then actually it is corresponding to 99th position. So it should be 99. So everybody, can you understand? So for electrostatic potential, we will have, for example, we will have 105 unknown variables. So 100th point is not exactly corresponding to 100th positions vortex's electrostatic potential. Instead of that, we have this one. Also, for example, if we say a little bit more question on this stuff, I see that is quite interesting. If we ask 105th component of our x vector, then what will be the answer? That will be just phi at 103. So, students, so please let me know whether you have all understood my question up to now, or my explanation up to now. So if we follow this kind of arrangement or assignment method, then you will have this physical meaning for each component, like first component, 100th and 105th. Okay, so could you please answer my question? Okay, thank you. Mr. Han, you told me that uh, the meaning of one x of the 100th element of our x vector, and I'm saying that that should be 99th point, not 100th point. So let me just draw once again, because now I just erased my previous drawing for this structure. So although the structure shown here is for 7 points example, but now I'm talking about 103 points example. Okay, so the considered structure here is like this. Here we have a vertex number 1, 2, and we will have more points like 3 and blah blah blah. And oh, sorry, let me just introduce. And we will have the end of a silicon region here, and that will be 102. And finally we will have the last point, and that will give you the number like this. So now we introduce 3 regions once again. Yes, yes, this is top oxide region, and this is bottom oxide region, and this is silicon. Yes, so following this way, then first let's assign our electrostatic potential on top of our x vector. So now we will have this kind of assignment. Okay, it will take, so phi 1 will take x1, and yes, this guy will have phi 2 at oxide, and that will have x2, and phi 2 at silicon, and that will have x3. So quite naturally, that will introduce phi 3, of course, at the silicon node, and that will have number 4, not 3. So if we go to, yes, now 99, think about certain 99th point, then that will give us 99th point electrostatic potential. However, that will be x100. That is my thinking for saying the answer should be phi at 99th point. So, Mr. Han, are you with me about my answer? And how about other students? So if you have all understood this situation, then please let me know. Okay, great, Mr. Jung. How about Mr. Park? So, of course, um, okay, good. Then, now, let's go to the second way of assignment. Then, in this case, it is still true that we have phi 1. However, now it becomes a little bit more complicated. Let's just follow it. So x1 will be phi 1, x2 will be phi 2 and oxide region. Then how about this guy? Phi 3, yes, oh sorry, x3 will be phi 2 and silicon. So I think that for upper part it is exactly same with previous one. Good, quite good, quite good. But think about this one. Even for this 105th one, we will have phi 1 oh sorry about that. I made a mistake here. Think about this one. We will have up to what? Up to phi. We will have phi 102 silicon. So here we have spent two unknown variables, and here we have spent 101 variables. After that, what comes? Now this electron density comes. So it is given as electron density and second node and electron density at third node. So our answer should be N3 instead of this electrostatic potential at 103rd node. So if you have any question, then please let me know. Then now let's go to the third method. Now electrostatic potential is first assigned in the oxide region. Okay, good. Then let's go to the next part, silicon region. In this case, we assign in that way phi 2 silicon N2 P2. Oh, now we assign three unknown variables for our how can you say our points, like the second point. Then let's consider 100. This one number 100 is given by 2 plus 3 times what? 32. So then we will have 2 more. So means that we will spend 32 points for this guy. So the first one is the second, and we will spend 31 more. So finally it will be 33 and 33 P33. So we will spend many 96 unknown variables to describe that information After that, we will have phi 34, phi n 34, p 34. So the answer now becomes what? Now it becomes n. Now it becomes n sub 34. Aha. Then if we go 5 steps further, then we will immediately find that this is 100 and 101 and 35 P35 and finally 36. So the answer will be 536. Whew, it was a long way. However, the reason why I just specify certain examples for our assignment. What is the meaning, physical meaning of x1, x100th, and x150th? The reason is it really depends on way of assigning your unknown variables. So nobody can provide you the automatic way or quickest way to find out the meaning of your quantities. So, for example, just to divide it by number of 3, then by collecting the remainder, so you can say this is electrostatic potential or hole density or electron density. If we have really something like this, phi n p, this basic routine is repeated in everywhere, then if we have 100 points, then we can decompose it into 3 times 33 plus 1. Oh, so it will be just a potential at 31st point. And if we have 105, then it will give us 34, 35. So it will be just 35th point and its hole density. So if we have just a regular pattern for our unknown variables for everywhere, then that will be quite easy to consider this one. However, unfortunately, we are now saying that this is not an efficient way to do that. So for each region, we have to say that this variable can be assigned or not, and their arrangement in our x vector can be arbitrarily done. So finally, our lesson out of this long discussion is now we have to keep the information about our unknown variables. So then you can think about this way. Oh, yes, if you ask me that question, that information, what is the physical meaning of x1 and x100 and x105th, then we have to keep not only the value of those numbers. So, for example, sometimes you can have something like this 0, 0 0.1, 0 0.2, blah blah blah. And since this is whole density, for example 10 to the 3, 10 to the 4, blah blah blah, you can have a certain realization of this vector. However, this number, numeric number, is not the only one you have to have. in reality, you have to understand what is meaning of this number 0. Depending on your way of arrangement, sometimes it can be 0 volt, or it can represent that you have no electron density at all, or it can means that you have no hole density at all. So keep the information. So are you all with me? Then let's think about this one. Now you solve the answer. Usually, so I will not talk about the Newton Raphson method, because at least our 3 students, enrolled students in this class, is know quite well about Newton Raphson method, because they have already studied the self-consistent Poisson equation solver. So I will not repeat it. Then usually what you get out of this procedure is the correction for your solution variable. So let's say that this is your temporal solution. Then usually by solving certain matrix equation, you will get a correction vector. So this is usually called a update vector. So you know it quite well. So now you have an update vector. Wow, good. But this is just given as a long column vector. Then actually you have to now update each variable. So it means that, oh, there is 307 by 1 matrix. So inside it, there is your update. Say that for electron density at 37 point, then please update it. There is somewhere for your update. Then how can you find out this quantity? Update for 37th point. Then you have to understand, actually, yes, if I wanted to find out this number, where is the points for my update? So here, then you can find a certain and 37. So simply speaking, for each variable in each region, you have to understand that for each region, each variable, so let me just write down, for each region and variable pair, we must know the index in the solution vector. Okay, that is main lesson in today's lecture. Okay, so I think that time is close to the end, so I wanted to just summarize today's lecture. Today's lecture gives two important lessons. One is, although it is not most efficient way, but if we have a certain interface point, then we have to define 2 or more variables for each region. So let's say that this is region number 1, region number 2, then we have to consider certain variable for region number 1 and region number 2. That was first point. And second one is, if you have multiple variables, then the arrangement in the solution vector x, it really depends on your choice. You have a freedom to do anyway. But the point is, now you must keep the information about your solution vector index. Usually my suggestion is, more important thing is, think about this one. You have x, and what is the physical meaning of x1? It can be avoided. So, however, this one is really needed. N55. Then what is the value for x sub x of 1? You have to understand this index. So I think that we are close to the end of our lecture. So in today's lecture, I wanted to give you a problem. The problem is just to reuse your previous code. Then please assign 3 dummy the dummy solution variable. Let's call it as A, B, C. Now you can assign 3 different unknown variables, A, B, C. Its name is A, whatever, okay. Instead of that, let's call it as A, triple A, triple B, triple C, 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 C. Then please assign this AAA variable over all your simulation domain. You know that this AAA, triple A, is an analogy of your, how can I say, your electrostatic potential. And for this BBB, please define it only on semiconductor regions. And for CCC, then please define it only your insulated regions. Then my question is not calculate something, just to construct a vector containing the information. Of course, you can arbitrarily set the values of this AAA, BBB, CCC. It's up to you. For example, you can say 0, 1, 2, or generate a random number, or any rule for assigning your AAA, BBB, CCC. Then just to construct the solution vector X. That is my suggestion. So, okay. Are you guys all with me? Do you understand the homework number 7? Simply speaking, introduce 3 variables which have all different rule for physical meaning. So AAA is valid for everywhere, and BBB is only have physical meaning for semiconductor regions, and CCC has physical meanings only on the semiconductor regions. Then by collecting them all, make a grand solution vector X. So I want to check everybody understand my homework problem. So please repeat that you have understood the homework problem, then I can wrap up. Of course, I will type my homework problem in our GitHub repository, but anyway, it's important for you to understand right now. Okay, Mr. Han, thank you. For example, let's say you have, for example, some of you have made this kind of a shape for your, let's assume that. Then you have introduced, for example, certain terminal, and internally you have divided it into this way. Let's say that this is a semiconductor and this one is oxide. Yes, and now your A variable is defined all over this shape, and your B variable is defined only for this one, and your C is defined only for this one. Actual value of AAA, BBB, and CCC, that doesn't matter. So please assign any arbitrary value for them. Then my question is just to build a X vector which contains full information about AAA, BBB, CCC. For example, you can assign in this way AAA, BBB, and CCC, or you can take different ways to arrange your quantities. But anyway, today's goal is just to build X vector. Then, of course, if I ask you what is the AAA certain vertex number, then you have to say that that is corresponding to X's certain index. You should provide this index for your AAA quantity, BBB or CCC. Okay, Mr. Han, so are you with me? I think that since the time is up, I should wrap up now, and I will just post my homework problem in our GitHub. Then please read it. Then if you have a further question, then please contact me through our Slack communication. Okay, thank you for your participation, and see you next Monday. Oh, not Monday, Tuesday. Bye.